Jnanam paramam dheyam. Knowledge is supreme.
So, now that we have learned how to mechanically arrive at the symmetries of normal modes, we want to see to what extent, without getting into the quantum mechanics, to what extent we can talk about what kind of internal motion. Internal motion means bond stretching and bending. We want to see what kind of internal motions give rise to what kind of symmetry. And since this is a spectroscopy course, we also want to know what kind, which of these vibrations are IR active, which of these vibrations are Raman active, which are inactive. That is the recurring thing of this course anyway. We want to know which transitions take place, which transition don't. Let us see how far we get to that in the remaining 20 minutes or so that we have. All right. See, how do I go about it? When we did the discussion of water, we could figure out the normal modes quite easily, right. So, now let us go one step back. Let us look at this stretch, individual stretches, let us use them as basis elements and let us see what kind of reducible representations we get. Let us use the bends as the basis and let us see what kind of reducible representations we get. And then we are going to tally with this and let us see where that takes us. So, what I will need to do is, I will need to write these E 2C3, 3C2, sigma H, 2S3, 3 sigma B. Have I written everything? Yeah. So, we are dealing with this molecule, say BF3. Let me call these bond lengths bonds L1, L2, L3 and let me call these angles, well, theta 1, theta 2, theta 3. Okay. So, what is gamma L1, L2, L3? Can we figure that out? So, I am now taking each bond, right, as a coordinate. So, when it stretches, it is plus L1, plus L2, plus L3. When it compresses, it is minus L1, minus L2, minus L3. So, what will be the character for E? What is the character for E? There are 3 coordinates, 3 coordinates, 1 for each, right. Remember, what is the matrix? 1 0 0 0 1 0 0 0 1. So, character is 3. Remember, character of E is equal to the dimensionality of the representation. What about C3? When I apply C3, what is the character? Okay, let us work out the matrix then. This is C3. Where does L1 go? What does L1 become if I apply C3? L2. What does L2 become? L3, what does L3 become? L1, L1 becomes L2, L2 becomes L3, L3 becomes L1. Simple. What will the matrix be in that case? Yeah, first row, second, third. What is the character? 0. And this is something we learnt already, isn't it? Rolling stone gathers no moss. So, once again, the coordinates that move from their position do not contribute to the character. That is all we need to remember. Okay. So, even without working out the matrix, we can actually work out the characters. So, this is 0. What about C2? Let us say I apply C2, this C2. How many coordinates don't move from their position? 1. Now, this is 1 coordinate. So, you are saying 2 because you are thinking of atom. Now, don't forget each bond is. So, L1, L2 and L3 are going to interchange. L1 remains in its own place. So, what will be the character? 1. What about sigma H? What will be the character for sigma H? 3. Nothing moves. S3? 0 because again they move from their places. See, you are getting the hang of it. What about sigma V? 1. Excellent. 301, 301. Okay. So, if you use that formula, you will see that it breaks down into A1 dash plus E dash. I am just giving you the answer to save time, but for what you could do is you could verify this answer quickly. You have the character table in front of you, add A1 dash and E dash and see whether you get 301, 301 or not. Okay. Now, if I try to make gamma theta 1, theta 2, theta 3, I want to use these 3, and now when I say theta 1, theta 2, theta 3, what is important to remember is that all these are in plane bends. Okay. What will the characters be for gamma theta 1, theta 2, theta 3? What is the character of E 3? What is the character of C3? Theta 1 becomes theta 2, theta 2 becomes theta 3, theta 3 becomes theta 1. 0. What about C2? 1 or minus 1? 1 or minus 1? I understand why you are saying 1, because if I apply this, theta 1 and theta 3 interchange, and theta 2, does it remain theta 2? Does it become minus theta 2? It remains theta 2. Why? Because this is theta 2, this is minus theta 2. It does not matter that the two bonds have interchanged. Don't forget what is the coordinate. It's very important to understand what the coordinate is. When the bond opens up, then it is plus. When the bond closes, it is minus, or the other way around, depending on how you define it. Okay. So, just because you have rotated it doesn't mean that what was going out will start coming in. It will still keep going out, right. So, character is 1. Sigma H, what is the character? 3. S3, S3 0, and sigma V, theta 1 and theta 2, 3 interchange, theta 2 is plus theta 2 or minus theta 2, what does it? Still plus. So, again 301, 301 is what you get, and again it breaks down into, I can write gamma theta 1, theta 2, theta 3 is equal to again A1 dash plus E dash. Is there any other kind of coordinate we can think of? So far, we have only talked about stretch of the bond, and we have talked about in plane bending. We can think of doming motion. We talked about doming motion in some context, I don't remember what. No? Yes. We discussed what a dome is. So, doming motion means what kind of a motion will it be? Let me draw it. Plus minus, minus, minus. This is one kind of motion, right? One, the three pendant atoms. So, I am going to use the term pendant atom quite often. So, this is a central atom and these are the pendant atoms. I hope you know the meaning of pendant, right? Pendant means something that hangs, right? You wear a necklace and then you put a locket in it, that locket is called pendant. So, that is the meaning of pendant. So, this is one kind of vibrational motion we can think, this is doming motion. What will be, so if this is called say xi 6, what will minus xi 6 be? This is one of the phases. What is the opposite phase? This plus phase I am defining as the central atom coming towards you, the pendant atom going away from you. What will the minus phase be? Just reversal of directions. Is that right? Right? So, what do I call it? I call it gamma dome. I am making up these names, right? I can write whatever I want, does not matter. What will be the character for E? 1, not 4, 1, because it is one kind of motion. The whole thing together is one motion. So, dimensionality is 1. Okay. Do not forget, this is plus xi 6, this is minus xi 6. This is one kind of motion. What is the character of C3? Think of this, this is C3, apply C3, does it remain xi 6, does it become minus xi 6? It remains xi 6, right. So, character is plus 1. What is the character of C2? Do not forget where C2 is, this is C2. Is the character plus 1, is it minus 1? For C6, is the character plus 1, is it minus 1? Lend me your pen, please. Lend me your pen, please. This is plus, this is C2. If I apply C2, it becomes like this, right. This is plus, plus xi 6, C2 means it will go behind, is that right. So, it becomes minus xi 6, character is minus 1. Whose pen is which? Okay, thanks. Are we convinced that it is minus 1? Minus 1. Sigma h, what is the character? Minus 1. S3, turn, does not change, then reflect with respect to sigma h, minus 1. Sigma v, plus 1 or minus 1? Plus 1. 1, 1, minus 1, minus 1, minus 1, 1. Is it there? Yes? Is it there in the character table? A double dash, and that is the one that is not taken, do not forget. So, your gamma dome, where do I write? Is equal to A2 double dash. Okay? See, another way of thinking is this, only this doming motion would be antisymmetric with respect to sigma h, right. In plane stretch, in plane bend, they would all be symmetric with respect to sigma h. So, just by looking at it, you can say that this doming motion has to be A2 double dash, because out of the symmetries that I have got, only A2 double dash is antisymmetric with respect to sigma h. Okay? Right. Okay? So far so good? What have we been able to say? We have been able to say that this A2 double dash is pure doming motion, and this A1 dash and A2 double dash, A1 dash and E dash seems to be mixture of in plane stretch and bend. But now we have a problem. What do we get if we add all of them? We get 2A1 dash plus 2E dash plus A2 double dash. So, no problem with E dash, no problem with A2 double dash, there is a problem with A1 dash. We have, so see, we need 6 coordinates, right? In fact, we have ended up creating 7. So, there is 1 coordinate extra, okay. That coordinate that shows up when you do this simple minded analysis is called a redundant coordinate. Where is that redundant coordinate hiding? Can you tell me where that redundant coordinate is hiding? One of these coordinates should be discarded. Which one? Yeah? And well, I will give you a hint. One of the A1 dash coordinates should be discarded because the number of E dash coordinates have tallied. The number of A2 double dash coordinate has tallied. There is one extra A1 dash. A1 dash, don't forget, is totally symmetric representation. We have somehow created a fictitious coordinate, a fictitious totally symmetric coordinate. So, we have to eliminate it now. Where is that coordinate hiding? Of course, you got A1 dash from the stretches and the bends. So, let us think a little bit. What would be the symmetric stretch? Everything expanding together? That can happen, no issue. But what would be the symmetric bend in this case? Theta 1 increasing, theta 2 increasing, theta 3 increasing. Is that ever possible? No, right? Because theta 1 plus theta 2 plus theta 3, if it is in plane, has to be 360 degrees. So, if theta 1 and theta 2 increase, theta 3 cannot increase. So, the whole issue is that we have taken theta 1, theta 2, theta 3 to be 3 independent coordinates, whereas they are actually not. Actually, theta 3 is dependent on theta 1 and theta 2. Okay? So, what we do is we happily delete one A1 dash from here. Okay? So, what do we end with? We end with one A1 dash vibration, which is a pure symmetric stretch. No contribution of any bending in A1 dash. We end up with 2 sets of E dashed coordinates, which are in plane motion, comprising of stretch as well as bend. And we have this doming motion, which has A2 double dash symmetry. Alright. And now I hope our discussion is sounding a little more like what you do in organic spectroscopy or inorganic spectroscopy, where they talk about stretches and scissoring motion and all, right. That discussion comes from this.